Good afternoon, everyone. Welcome to the Christmas session of the seminar. We have, as a present, we have a speaker from currently the Computer Science Institute of Academy of Sciences, Frederik, who will tell us something about matching in hypergraphs.
Thanks a lot. Thanks for the invitation. So let's bring the Christmas spirit and talk about hypergraphs. But first, let's recall what an ordinary matching is in a graph. So what was a matching? A matching in a graph is just a collection of edges, right? So it's just you have edges E1 up to En in some edge set of some graph G, and you want that they are pairwise disjoint. So they don't intersect for all not equal to J, right? So you have your collection of edges living in some graph, and they don't intersect. Okay, so far that is a matching. And then what will people care about? I mean, what is the thing you can do, what you want to maximize? Because you force them to be disjoint, you want to maximize how many you can have, how large this matching can be, how many edges you can have. So this is the matching number, nu of G, and this is then the maximum size of a matching in G. Okay, this is something people analyze. And then a related kind of dual notion to that is the vertex cover. Yeah? There's also something dual one can do, and this is looking at the vertex cover. And what is a vertex cover? A vertex cover is now a set of vertices, and a set of vertices in G, such that every edge meets the set of vertices. So you fix some set of vertices. If you compare to any edge of the graph, the intersection with the set should be known. Then this is a vertex cover. And what do you want to do now? Well, for vertex cover, you're interested in minimizing, right? Because, of course, it's very easy to find a vertex cover by just taking all vertices. Then you cover also all edges. And so the question here is that you want to determine the vertex cover number of G, and that is the minimum size of a vertex cover in G. I actually find, I'm not so sure how happy I'm about the name vertex cover. I think you're actually covering edges somehow, right, by using the Yeah, but I don't like it. So you can like it, it's fine. Okay, and then a quite immediate observation about this is that you can sandwich the vertex cover number in between the matching number. And so by saying that tau of G, first of all, this is lower bounded by the matching number. Because if you want to cover all the edges of the graph, if you take a maximum matching, then you need to have in your vertex cover a vertex from each edge in this maximum matching, otherwise you don't cover everything, right? So this gives you a lower bound. And then you can also use this as an upper bound, a trivial one, so by 2 times nu of G. Because you can just take all the vertices of the matching, and now you must cover, if it's the maximum matching, you must cover all the edges, because if there was an uncovered edge, then you could just add it to this maximum matching, and you would have a larger matching, right? So in this sense, this also gives you an upper bound. So lower bound, just take a maximum matching, take every vertex, take one vertex from each edge. Upper bound, take a maximum matching, and then you have all the vertices. Okay, so this is a kind of the observation, and then there's this classic König theory, which you learn in a graph theory class, that if you restrict to bipartite graphs, if G is bipartite graph, then you actually get a better upper bound, and you can actually bound it by tau of G is bounded by nu of G. Yeah. So you remember this probably if you had some graph theory course. This is a classic theory. Okay, so now let's talk about hypergraphs. So this was the situation in graphs. So let's look what is in hypergraphs. So what is an R-uniform hypergraph? R-uniform hypergraph. This is like a graph. It's a set of vertices and edges. And now the edges are a subset of K sets of the vertex set. Right? So now, instead of pairs of vertices, R sets, right? Sorry. This is always, sometimes people use R uniform and K uniform, and then one gets confused. And I actually am a K uniform person, and I don't know why I'm sticking with R uniform. So I will probably make it wrong all the time. Yeah, so instead of pairs now, we look at these triples of this is a 3 uniform hypergraph now, which has 3 edges on this vertex, right? So this is this generalization. And now I can make that this observation holds in straightforward with exactly the same arguments, exactly the same way. I mean, first of all, now we can also define a matching, of course. So this here is not a matching, but 2 disjoint edges give me a matching. Yeah, so we can define straightforward what is a matching. We can also define what is a vertex cover in the same way. So it works exactly the same. And then we can also make exactly this observation. And then just with one change. And here I said we take all the vertices of an edge. And for graphs, in the 2 uniform coordinates, this is always 2. But now in R uniform, an edge has R vertices, right? So there's one slight change here. So the observation now looks like nu of H. H is obviously an R uniform hypergraph now. Sandwich is here top of H, and R times nu to H. This is the trivial observation here. And now one is, of course, wondering, well, what about this analog here? What happens in graphs? Is there some similar phenomenon in hypergraphs? So for that, we need the notion of being r-partite. And this means that this R uniform hypergraph can be split, the vertex set can be split into R sets. So we can write V of H as V1 union VR, such that if you look at an edge of your hypergraph, it will intersect each of the partite sets in exactly one vertex. Yeah, so it looks something like we have in a 3 uniform hypergraph, we have our 3 vertices sets, and every hyper edge looks like this. This is a straightforward generalization to when we had a bipartite graph, like this. Okay, and then there is the obvious question: does something similar hold? And this was formalized by Ryser. So this is known as a conjecture by Ryser from 71. And it says that if H is an r-partite R-graph, so R-graph for short R uniform, then we have that the vertex cover number is bounded by R minus 1 times nu of H. Yeah, so that you can improve this R here by R minus 1, which coincides then with the graph case with König here. So that was this conjecture. And this is kind of a well-known often conjecture since then. So it is known for R equals 2, obviously, because this is König. And then it was also proven for R equals 3 by Aharoni in 2001. But that's it. Yeah? So all other cases are open, and we don't know. Okay, if I asked you to prove this conjecture, what might you do, right? So, like the first obvious proof idea, maybe, is that you would want to try some kind of induction. Yeah, you want to try some kind of induction. So, what if you could find R minus 1 vertices in H, which if you remove them, the matching number drops by 1. Then this is what you would want to do, right? So you would ideally you would want to do remove R minus 1 vertices such that then you get a graph H prime, and then the matching number of H prime is strictly less than what you started with. And if you could now do this iteratively, right, then you could prove this here, because all the removed vertices, they would just be your vertex cover. Right? Because in the end, you must be left over without an edge, so you must have covered all the edges with these vertices. Yeah, so you just repeat this. So repeat until this is empty, and the removed vertices form the vertex cover. We don't have edges. Yes. And you know, you only need so many iterations if you can always do that. Right? But this is somehow the big leap here. This here, can you do this? Right? If you can do it, nice, we have a proof of Ryser's conjecture, but can you actually do that? And that was Lovász question. So Lovász conjecture from 75 is H r-partite r-graph, then there exists this set of vertices such that the set of S is r-1, and if you remove it, the matching number drops. Okay, and yeah, so I think the motivation is clear why he asked it, and it's kind of the most obvious thing you could wonder. And it also is true for I equals 2, because you can use König's theorem to do that. However, it is not known for I equals 3. It does not follow from our Aharoni's result for I equals 3, if you think for it, about it for a moment. So this is known I equals 2 due to König. But for I equals 3, it's really a truly stronger conjecture, which is then still open. Okay, so that's the setting, and now this is the conjecture we care about. So I need some space, and you can think if you have some question.
So let me ask. So this Ryser's conjecture is like tight. There are no known examples that this r-1 is the best you can get.
Yes, there are versions. So you look at some projective planes or constructions coming from projective planes, and you do something with them, and then you can show that this is right. Okay. But these are not like so obvious examples, like just drawing a bipartite graph or a tripartite graph. But yeah, they are constructions. Okay. Indeed. So one cannot hope for more than that.
You can move the table up.
Yes, I can also move it up. Sure. Ah, right. There's another one. Thank you. Excellent. That makes it better. Let's use all the space we have. Okay, so this is the conjecture we care about, and it will not work for long, maybe. And now, very recently, there was an answer to this for I equals 3, and this is due to Clow, Haxell, and Mohar. And they proved now this in the spring. They found that Lovász conjecture is false for I equals 3. So I just call this now LC. So LC is false for I equals 3. So what they have is so they found a counterexample which is a line hypergraph. I will explain what this is, of a graph with 102 vertices. So it's quite a large example, and then they use the paper to analyze this graph and to prove that it is actually a counterexample to Lovász conjecture. Yeah. So what's a line hypergraph? A line hypergraph for an R regular graph. Graph G. So we define hypergraph L by the vertex set of L with the edges of G. And now I have to tell you which edges form hyperedges. So the edges of G will become the vertices in the hypergraph. And now the edge set of L are all incidence sets to the vertices V in G. And what's an incidence set? Well, an incidence set are just all the edges such that the vertex is in the edge. Yeah? So let's make a drawing for that. Let's say we have a 3 regular graph here. Something like that, something like that. Now, in my line graph, the edges will become the vertices. And now which we form hyperedges. Now let me do some of the colors here. So this edge, and this edge, they will become vertices in the line graph. And if they're incident to the same vertex, they will form a hyperedge. So those 3 edges here now form a hyperedge. And the same with this, those 3 now form a hyperedge. Yeah, now you see that this is the line hypergraph here, intersecting at this one vertex here, right? So this way we can construct from an ordinary graph, a hypergraph. And yeah, the remark is that if V is R regular and R edge colorable, then the line graph is a r-partite R graph. Right? That it's an R uniform graph. This is quite clear if it's R regular, because then you have R edges in the graph which form the hyperedge. So this is why it's and if it is R edge colorable, well, then this edge coloring gives you a vertex coloring in the line graph, which gives you the partite sets. And you can only have edges in between because they must always come from different color classes when they touch in a vertex. And the only hyperedges we add are the incidence sets to a vertex. Right? So this way we get examples for what we're actually looking at. Now I think you can see the connection. So the only thing is that one needs to prove that it violates Lovász conjecture, right? But it's the right object now we are talking about. Okay, so let me make one other definition. And now what do I do now here? Is this the best way to pursue? So then let me talk about a graph class, which is called the generalized Petersen graph. You all know the Petersen graph. So you draw 2 circles of 5 vertices. One is really a circle like this, and the other one you go to every second. You connect every second one, and you also connect these spikes here, or rungs. Yeah? So this is a Petersen graph. If I ask you to generalize it from 10 vertices to 20 vertices, but you want to have kind of the same graph, there's one kind of obvious way how you would want to do it, right? So you take cycles which are bigger. So you take longer cycles, you put the cycle inside, you connect them up, and now you have the outer cycle, and then you have this inner one which is always jumping over to the second one, and either this forms one cycle or it forms 2 cycles. Right? So obviously this is how you would generalize this, and this is called GP N And then you can, instead going to the second, you could also go to the third, so this would be k, but we actually only care about this being 2. So this is called the generalized Petersen graph. And then, now our result is theorem together with Aida, Xavi, and Christoph, also this year, that this generalized Petersen graph gives you an infinite family of counterexamples to Lovász conjecture. So the line graph, line hypergraph of GP 5k plus 11 2 is a counterexample. Is a counterexample to Lovász conjecture for all k. That's the reason why I don't use k for the uniformity, but I should have maybe swapped this with L. Yeah, so that's our result. So we can deduce an infinite family, and it's even a quite easy one. I mean, it's a very simple graph, right? And it's also, let's see how much time I have, we can even analyze it quite humanly, directly, simply, and see that it's a counterexample. Yeah. Maybe I mention it now, but then I'll say maybe later about what the changes. But then we also have another theorem, same people, and that is that we also found a counterexample for r equals 4. Yeah, but that is not such a nice family, but we found one with computer systems. Yeah.
So the first theorem is for r equals 3.
Yes. So the Lovász conjecture for rk, and this means r equals 3 because it's a 3 regular graph. So it's not for r equals 3, but yeah, thanks for pointing this out. Exactly. So, and the other theorem is that we have found one counterexample to Lovász conjecture for I equals 4. Okay. So I can take the time if there are any questions. Otherwise, I can. Oh, this is quite good with the time, so I can go to explain a bit about the proof why this works. Yeah. Yeah.
The graph on 102 vertices, is that also coming from a Petersen graph?
No, it is called Big Smith graph.
So how large is
102 vertices. Like, yeah.
102 edges?
I didn't know it before, and then it's quite involved to analyze it because it's still quite a big graph. So even if you say you just want to check this property, right? I think they still put some work into checking this property.
Is the example for r equal to 4 also coming from a graph construction?
This is also coming from a graph construction. It's also a line hypergraph, but now a bit you need to go for a regular graph. Yeah. But exactly. And we found this by computer search. Here we also got an intuition with computer search starting, and then we swapped to proving it. Yeah. Exactly. Okay, yeah, so these are these funny graph classes, right? Generalized Petersen graph. We were a bit wary. Sometimes you have to be political about when you write your abstract and your introductions, right? So, and if you want to submit your paper to the people, so if you write a paper, and we are doing funny things with the generalized Petersen graph, you must try to avoid maybe that editors have some prejudices. So we just formalized it as we are talking about the Lovász conjecture, right? And then it happens to be the generalized Petersen graph. But it's actually quite funny that the fact that people looked at this generalized Petersen graph class, we use a lot of properties people investigated, right? And now these properties are useful to tackle some, I think, quite serious conjecture from extreme graph theory. So I think it's sometimes funny that also looking at just some graph class, which itself seems a bit maybe not overwhelmingly interesting, then results into interesting consequences. So, yeah, so let's explain how this works. So basically, the fundamental way how to check this property is the following lemma, which is also implicitly used by Clow, Haxell, and Mohar, and this is basically the idea. And this is the following lemma. So how do we check now for this line hypergraph that is a counterexample? So if G is R regular and R edge colorable, if the independence number of G stays the same if you remove all the vertices from some collection of edges. So this stays the same for all subsets G with the subset of the number of edges we look at is R minus 1. Then the line hypergraph of G is a counterexample to the Lovász conjecture. Yeah. So that is basically what it's based on. And then this is a property now, because now you convert it into a nice graph property, right? That you look at this graph and you just have to check this property for a graph. Analyzing graphs is way easier than hypergraphs, and this is now a handy thing. Okay, so why is this true? Well, we have to check that it violates Lovász conjecture if we can assume this for some graph G. So what do we have to look at? We look at some subset of the vertices of the line graph. Right? And this is an arbitrary subset, and this has size R minus 1. And now we can use this property star here. We assume this property star. Yeah? So from this property star now it follows that there exists an independent set in G. So it's a maximum independent set such that it avoids all the vertices from this edge set. Yeah? Such that E intersecting E equals the empty set for all edges in S. Right? Because the independence number stays the same, so we find one maximum independent set which avoids these when we delete this. And this is a union of the edges here, right? So I'm removing the vertices, all vertices which are appearing some edge. And then I want to convert this into a matching in the line hypergraph. And there is an easy way. So this gives us a matching MI, and this is just all the incidence sets to all the vertices in the independent set. And this is now a matching in L because these are independent sets, right? So there's no edge in between two elements of I. So if we go to the line hypergraph, if we go to these incidence sets, one for A and one for A dash, they cannot share the same edge because otherwise we would have an edge in the independent set, which we don't have. So this is how we get a matching in L. And this one is also avoiding S. Avoiding S. Well, but then we have now that if we look at the matching number of L minus S, then we still have this matching we have still in L minus S this matching. So we have that the matching number stays the same. And this is now for every set of R minus 1 edges, right? This was an arbitrary choice. So Lovász conjecture is not true because if you find such a graph G with this property. Because you cannot find R minus 1 vertices you can delete from this hypergraph, and you drop the matching them. Yeah, and the argument is just about switching around between this independent set and the matching you get in the incidence, with the incidence sets. So this is the lemma, and now the work is to check that this graph class actually has these properties. Now I have to erase something. And I think all of that we know now. We only need to check the lemma now, right? So this can all go. And we know what to do. Know what matching is. Okay, yeah, so we need to build on some things people found out about these generalized Peterson graphs. So it is useful, for example, that they know that it is three-colorable, three-edge colorable. So this is Castagna and Prince, 73. And there we already know that the general Peterson graph is three-edge colorable. You can also play around with it yourself and convince yourself that it is three-edge colorable.
For which line?
Yeah.
Yes, for our length.
Yes. Do you know like the classification?
I don't have it here now. No, sorry, but I can give you the reference. So.
Oh, you gave it.
Yes, you can Google it. But okay, it's three-edge colorable for our. So let me be precise about our. N is 5k plus 11. So it is three-edge colorable. So what we now need to show, and obviously it is also three regular. So we have already the two conditions here. So we need to show this star condition, right? We need to show that if we look at the independence number from this generalized Peterson graph, and now we remove four vertices which come from being two edges. And if then the independence number always stays the same for all edges UW, UV, WH, and G. Yeah, this is what we have to show. Right? So let's call this star. It's the only thing we have to check. Then we're done with our lemma. And for this, we use some facts. For example, another fact which was proven by Fox, Gera, or Gera, no, Stanica, in 11 is what is actually the independence number. It's quite useful to know, right? So the independence number of this general Peterson graph 2 equals 4n over 5, rounded down, for all n at least 5. This is a result we will use. Another result, which they also show, but which is also pretty obvious, is that we will look at the independence set a number if I just restrict my graph to such a subpart of the number of rungs considered. Let's call this a rung, a pair which is connected like this, and we will look at consecutive rungs. And for that, it will be helpful that you know that the independence number of 2, if we look at something like SI5, then this is at most 4. So what do I mean by SI5? I mean we have some index I here, and then I take 1, 2, 3, 4, 5 consecutive rungs. So this is SI5. And this induced subgraph of those 10 vertices. This can of course start anywhere in your long generalized and yeah, you can see that you can only find an independent set of size at least 5 there if you try to play it around, because you will block yourself. Obviously, it cannot be more than 5 anyway, but you cannot even do 5 because one will be blocked. It's not very deep. And then a third fact also not very deep. If you make this large enough, your Peterson graph, if we make this long enough the cycle, and you mark two edges, your v, wx, then you can find at least a rung of length 10, which does not intersect those two edges, which is kind of obvious, right? So let's write this down. And for this, you need n at least 26 to work, and then there exists some index L0 element Zn, such that if you look at the vertices from these two edges, then they don't intersect 10 consecutive rungs. Yeah? So that's our situation. So this is another thing we will use, and then we can do the proof. Okay, how does the proof work? The proof is induction on K, and we start with K equals 0, 1, and 2, so that this n goes up enough. You can start checking this even by hand if you really, really want to, but I mean, you can also just write a computer program and you have immediately check it. That it holds for that. So let's say computer. And now induction on K. And what do we want to do? The first thing is find such an Si010 like in F3. So let me maybe now draw a picture. So I want to use a new color. Maybe let's use a black one. Let's draw a picture now what we're going to work in. So we have this generalized Peterson graph, and it is just a long cycle, and the second long cycle. They're connected like this. Like that. Outside we just have the cycle. Inside we always connect to every second one, right? Like this. And now what we want to find is 10 consecutive ones which do not intersect our two edges. So we have these two marked edges which will be removed. Let's say they lie somewhere here. They could also connect, by the way, but they are somehow outside. If it's large enough, we find this consecutive rung, series of rungs which does not intersect it. Okay, so let's say like this, and let's call this an minus 9, an minus 8, an minus 7, an minus 6, an minus 5, minus 4, an minus 3, an minus 2, an minus 1, and and then we have one more here. This, and this is what we cut out. This is now our I10. Okay, so we found this. Now, second, we remove where do I continue by? Continue right now the next board. Now we remove 5 of those rungs, the last 5 ones, because we want to use an induction, right? So basically we want to go down to a smaller generalized Peterson graph and then use the induction hypothesis on that. So we just remove a couple of the rungs and then we have a smaller, and then we turn it into a generalized Peterson graph. So second thing is remove the rungs n minus 4 up to n, right? So what we remove here, this we just remove. And then we just connect those up. Now we have this hole here, we connect the hole up like you do in the generalized Peterson graph. So this will be connected to this one, this will be connected to this one, and this one will be connected to that one. And then we just have cut it out and we have a smaller generalized Peterson graph. So this is remove rungs and then connect an minus 5 a1, bn minus 5 b2, and bn minus 6 b1. And now we just have a smaller generalized Petersen graph, so we get our G prime, which is GP. And now, okay, if we started here with G equals GP 5 times k plus 1 plus 11, now we we reduce the size by 5. So now it is 5k plus 11. So we have our induction hypothesis, and we can find this independent set, which avoids these vertices of those two edges, right? Because this is what we're actually trying to find. We're trying to find an independent set here, maximum independent set, which avoids this orange vertices. So this gives us I tilde, and this is in the vertex set of G prime, and this is independent set with of the following size. Well, we know by fact 1 what the size of the maximum independent set is, and that is 4 times 5k plus 11 divided by 5. And then, well, this is just 4k, and 44 divided by 5 is 8, obviously. And then we have that the independent set also does not intersect any of these orange vertices. Yeah, this we just get by induction hypothesis. Nice. So obviously the step now is how do we get independent set in the original graph? So we have to add something. This will also give us kind of a starting point for independent set in actually the big graph G without this cutting off. But we need to manipulate it a bit to get it now bigger, because we want it to be for 5 times k plus 1, the number of the size of the independent set. Okay, and for that we use the following fact 5 now, well, the fact we already mentioned. If we now look at this independent set and the intersection of the rungs n minus 9, n minus 8, and so on up to Rn minus 5, then this is at most 4. This was one of the facts we mentioned, fact 2. And this means there exists some index I1 such that R1, RAI1, this is a rung at coordinate I1, that this is not intersecting the independent set. Yeah. So let's show it in the picture. If we look at the first 5 ones, we know that only 4 of them can intersect the independent set, only 4 of these rungs. So let's assume now for the sake that this one is not intersecting the independent set. So this is my I1, and this one does not have an element of the independent set. Now the question is, how do I use this to manipulate, to complete my I tilde to an independent set of G? So this one here might contain a vertex in the independent set. So let's assume it was this one here, right? So what am I going to do now? I'm going to move this one in the end. So I'm going to move this one here. Why will this work, or why is this a good idea? This stuff here was connected to what follows when we use the induction hypothesis. So I made sure that this cannot clash with another vertex which is in the independent set following here, right? So if I move it here now in the big graph, this is also fine, because this is connected the same way this was connected. So moving this here is a legal move. I'm still in the independent set now in the big graph. So that's the first thing. And now I want to add 4 more vertices to the independent set. And which one am I going to add? Well, I'm going to add this one, this one, this one, and this one. Yeah. And now I have to check that this is still independent. This works well because I knew that this one is not intersecting the independent set. So I can add this one without creating any problem. Now this is cleverly chosen that they don't block each other here, right? Because they are not connected. This is not connected to this one. This is all fine. And this one we are leaving free. So there's no problem, even if, I mean, I just arbitrarily said this is an independent set. It could also be this could have been it, but then I do exactly the same. I just move this here. And this will also work. It's not a problem. And yeah, that's basically it. Right. So we found four more vertices we can add, and it works. Now, I also made this arbitrary decision that this one is the rung which does not intersect. It could be that one or that one, but then you move everything just in the end. Like, instead of just moving one rung, we can also just move two of them in the end. And then you can do the same, and you can check that this actually also works. So that, yeah, that's the idea. So it's relatively simple. You cut out a couple of rungs to go to the induction hypothesis. You go, and then you take these independent sets, avoiding these evil vertices, and then you go back to the big one and you add 4 convenient vertices. But of course, we have to check now that the numbers work out. Right? But that 4 is exactly the number of vertices we have to add. But that's a quick calculation. So yeah, that's the argument here. 6. Move vertices Ri with I larger than I0 to the end. Right? That was this way I said that we move this here. If this was 2 rungs, then we would move these 2 rungs to the end and add 4 more vertices. As marked, and then we get the set I, independent in G, and the size of I is now what? The size of I is 4k plus 12, and that is the same as 4 times k plus 1, 4 times 5. 4 times 5, k plus 1 plus 11 divided by 5. Turn it down because this is 4 times k plus 1 plus 8. This is what we needed to show, that the maximum independent set, the size of the maximum independent set still stays the same, even after removing these two edges. Right. So yeah, it's a quite a simple neat proof. And that's it. Okay. Yeah, okay, time is also up. As I said, the obvious thing you're going to do now is you look at graphs which somehow look similar to this. So you do some funny changes that you can maybe, we call it generalized Cayley generalized Peterson graph, in which you use some group structure and then you create funny circular graphs like that. And then you do computer searches, they also violate, and then you can generate a couple more counterexamples. So we have some finite list of more counterexamples for I equals 3. And then you generalize it a tiny bit more that you can also do 4 regular graphs. And then you also find by computer 1 counterexample for I equals 4. But we did not find like a nice family for that. So I mean, obviously it would be really nice to have an infinite family for I equals 4 and for general R even, right? That would be the ultimate goal, and not, but we only have this for I equals 3 now, but at least that's something. And yeah, future work would be nice. Okay. Thanks a lot.
Are there some questions?
How big is the example for us?
40 vertices or something. It's not super clear. Or did I write it down? 70 vertices.
What is the group it's coming from?
For what?
And it's coming from some group, I assume, like if you're doing generalized scale.
Yeah, well, it's not really a Cayley graph in the sense. This is a funny thing we do. So I think it's not something amazing, something that N or that. I did not give the definition for what we mean by this generalized. Yeah.
is 22 vertices the smallest number of vertices in a cubic graph?
Yes, it's the smallest we found, and this is also how we started to find it. They were restricting their search, I think, of course, like Clow, Haxell, they also found it by computer search, and the way they had some restrictions, I think, to transitivity and so on. I mean, the problem is you run out, you cannot just check all vertices, all graphs, and then you cannot get not far enough. But yeah, their restrictions avoided this one. We were a bit more generous, so we could find it, and then we looked at it sharply, and then we thought, well, this should also work, right? Yeah, so I think we did a general search until 22, and we did not find anything else. Or did we really look at scroll graphs? I'm not sure. We can look this up. Yeah.
Yeah, I wanted to ask. So this is not a counterexample to the original Ryser's conjecture. Right?
No, because it's impossible. Because for I equals 3, it's true, right? So the one for I equals 4 could have been a counterexample to Ryser. We checked; it wasn't. That would have been amazing. The paper would have exploded in value. But unfortunately, that still stands. So,
yeah, but it shows that this is not a way to do it. Okay.
Well, I mean, yeah, this is not totally excluded the possibility that there could be some, that you could find, if Ryser was not true, maybe for higher uniformity, for some funny reason, there could be a graph which violates Lovász conjecture and also violates Ryser. But yeah, there's no reason to assume it.
Well, it's right there. Also
If there are no more questions, then thank you very much, Frederik, for Christmas.